OAuth 2.0 Authorization Code Flow with PKCE. Welcome to the channel. Please consider subscribing. I produce videos daily, covering a wide variety of cloud topics, with a focus on networking. Also, hit the bell icon to get notified of new videos. Today we are diving deep into OAuth 2.0 Authorization Code Flow with PKCE, which stands for Proof Key for Code Exchange. This is the most secure OAuth 2.0 flow available today and is recommended for all types of applications, including mobile apps, single-page applications, and even traditional web applications. OAuth 2.0 is an authorization framework that enables applications to obtain limited access to user accounts on an HTTP service without exposing the user's password to the application. The authorization code flow with PKCE was specifically designed to address security vulnerabilities in mobile and public clients where the client secret cannot be kept confidential. Traditional OAuth 2.0 flows relied on a client secret that had to be embedded in the application code, but this secret could be extracted through reverse engineering or network interception. PKCE eliminates the need for a client secret by using a dynamically generated cryptographic challenge that proves the same client that initiated the authorization request is the one exchanging the authorization code for tokens. In this presentation, we'll walk through every single step of the OAuth 2.0 authorization code flow with PKCE, including the exact HTTP requests with all query parameters, the cryptographic operations for generating code verifiers and challenges, the complete redirect flows, and detailed examples of access tokens, ID tokens, and refresh tokens. We'll examine how each token is structured, what claims they contain, and how they are validated. Most importantly, we'll explain exactly how PKCE prevents authorization code interception attacks, which is the primary security threat this extension addresses. OAuth 2.0 Core Concepts. Before we dive into the authorization code flow with PKCE, let's establish the foundational concepts of OAuth 2.0. OAuth 2.0 defines four key roles that participate in the authorization process. Understanding these roles is critical because each role has specific responsibilities and security requirements that shape how the entire flow operates. The resource owner is typically the end user who owns the data or resources being accessed. For example, if you're building an application that needs to access a user's Google Drive files, the user is the resource owner. The resource owner has the authority to grant or deny access to their protected resources. The client is the application requesting access to the resource owner's resources. This could be a mobile app, a web application, or a single-page application running in a browser. The client must be registered with the authorization server before it can participate in OAuth flows. The authorization server is the system that authenticates the resource owner and issues tokens after obtaining proper authorization. Examples include Google's OAuth server, Microsoft Azure AD, or Auth 0. The authorization server is responsible for verifying the identity of the resource owner through various authentication methods, like passwords, biometrics, or multi-factor authentication. After successful authentication and authorization consent, it generates access tokens, ID tokens, and refresh tokens. The resource server hosts the protected resources and accepts access tokens to authorize requests. For example, the Google Drive API is a resource server that validates access tokens before allowing file operations. These roles work together in a choreographed sequence to enable secure delegated access without sharing passwords. The OAuth 2.0 framework defines several grant types, but the authorization code flow with PKCE is the most secure and versatile, suitable for all application types from mobile apps to server-side web applications. PKCE Enhancement Overview. PKCE, which stands for Proof Key for Code Exchange and is pronounced PKCE, is a security extension to OAuth 2.0 defined in RFC 7636. It was originally designed to protect mobile applications from authorization code interception attacks, but its effectiveness has led to it being recommended for all OAuth 2.0 clients, including web applications and single-page applications. The fundamental problem PKCE solves is the vulnerability that exists when authorization codes are transmitted via redirects through potentially insecure channels. In a traditional authorization code flow without PKCE, an attacker could intercept the authorization code during the redirect from the authorization server back to the client application. This is particularly dangerous on mobile devices where malicious applications can register custom URL schemes and intercept redirects intended for legitimate applications. Once an attacker has the authorization code, they could exchange it for access tokens if they also possess the client secret. However, since mobile and public clients cannot securely store client secrets, this creates a significant security vulnerability. PKCE addresses this vulnerability by introducing a cryptographic challenge response mechanism that binds the authorization request to the token exchange request. Instead of relying on a pre-registered client secret, PKCE uses a dynamically generated, single-use cryptographic proof that only the client that initiated the authorization flow can provide. Here's how it works at a high level. Before starting the authorization flow, the client generates a random string called a code verifier. This code verifier is a cryptographically random string between 43 and 128 characters long. The client then creates a code challenge by applying a transformation to the code verifier, typically using SHA-256 hashing. The code challenge is sent to the authorization server during the authorization request, while the code verifier is kept secret on the client. When the client receives the authorization code and attempts to exchange it for tokens, it must provide the original code verifier. The authorization server then verifies that the code verifier, when transformed using the same method, produces the code challenge that was provided in the initial authorization request. If the values match, the authorization server knows that the client making the token request is the same client that initiated the authorization flow. An attacker who intercepts the authorization code would not have the code verifier and therefore cannot successfully exchange the code for tokens. This elegant mechanism provides strong cryptographic proof without requiring client secrets, making it perfect for public clients while also enhancing security for confidential clients. Complete Flow Overview. The OAuth 2.0 Authorization Code. Complete Flow Overview. The OAuth 2.0 Authorization Code Flow with PKCE involves a carefully orchestrated sequence of HTTP requests, redirects, and cryptographic operations between all four OAuth roles. Understanding the complete flow from start to finish is essential before we dive into the details of each step. The flow begins with the client application and ends with the client successfully obtaining access tokens that can be used to access protected resources on behalf of the user. The flow consists of 8 main steps, each with specific HTTP requests and responses. First, the client generates the PKCE code verifier and code challenge. This happens entirely on the client side before any network communication occurs. The code verifier is a cryptographically random string, and the code challenge is derived from it using a hash function. Second, the client redirects the user to the authorization server's authorization endpoint with a complete set of query parameters including the client ID, redirect URI, requested scopes, response type, state parameter for CSRF protection, and the code challenge along with the challenge method. Third, the authorization server authenticates the user. This could involve username and password entry, biometric authentication, or any authentication mechanism the authorization server supports. The authorization server may also leverage existing sessions, so users don't have to log in repeatedly. Fourth, after successful authentication, the authorization server presents a consent screen to the user, showing what permissions the client application is requesting. The user can choose to grant or deny these permissions. This consent step is crucial for user privacy and transparency about what data the application will access. Fifth, if the user grants consent, the authorization server redirects the user back to the client's redirect URI with an authorization code as a query parameter. The state parameter is also returned so the client can verify it matches the original request. Sixth, the client extracts the authorization code from the redirect URL and validates the state parameter to prevent CSRF attacks. Seventh, the client makes a backend request to the authorization server's token endpoint, providing the authorization code, redirect URI, client ID, and critically, the original code verifier. This is where PKCE verification happens. Finally, the authorization server validates the authorization code, verifies that the code verifier hashes to the original code challenge, and issues access tokens, ID tokens, and optionally refresh tokens back to the client. Each of these steps involves specific HTTP methods, headers, and parameters that must be precisely formatted. In the following slides, we will examine each step in exhaustive detail, showing exact HTTP requests with real parameter values. Step 1. Generate code verifier. The first step in implementing OAuth 2.0 with PKCE is generating the code verifier, which forms the foundation of the PKCE security mechanism. The code verifier is a cryptographically random string that must meet specific requirements defined in RFC 7636 to ensure sufficient entropy and security. This random value will be kept secret by the client throughout the authorization flow and only revealed during the token exchange step to prove the client's identity. According to the PKCE specification, the code verifier must be a high-entropy cryptographic random string with a minimum length of 43 characters and a maximum length of 128 characters. The allowed character set is limited to unreserved characters defined in RFC 3986, which includes uppercase letters A through Z, lowercase letters A through Z, digits 0 through 9, hyphen, period, underscore, and tilde. This character restriction ensures the code verifier can be safely transmitted in URLs without encoding issues. The 43-character minimum ensures at least 256 bits of entropy, which provides strong security against brute force attacks. Let me show you how to generate a code verifier in several programming languages. In Python, you would use the secrets module, which provides cryptographically strong random number generation. The secrets token_oSafe function generates a URL safe random string, and we specify the number of bytes. Since Base64 encoding produces 4 characters for every 3 bytes, we need 32 bytes to get approximately 43 characters. The resulting string will be between 43 and 128 characters. In JavaScript for web applications, you use the WebCrypto API, which provides cryptographic operations. First, generate 32 random bytes using crypto. Get random values with a uint8 array, then encode these bytes to Base64 using BTOA, and finally make it URL safe by replacing plus signs with hyphens, slashes with underscores, and removing equals signs. In Java, you use the secure random class, which provides a cryptographically strong random number generator. Generate 32 random bytes, then encode them to Base64 using the URL safe encoder without padding. The code verifier is generated once at the beginning of the authorization flow and must be stored securely on the client. For mobile applications, this means storing it in secure storage like iOS Keychain or Android Keystore. For web applications, it can be stored in session storage or memory, but never in cookies or local storage where it could be accessed by malicious scripts. For single-page applications, storing it in memory is best practice. The code verifier must remain secret until the token exchange step, where it will be sent to the authorization server to prove that the client making the token request is the same client that initiated the authorization flow. Generate code challenge. Once we have the code verifier, the next step is to generate the code challenge, which is a transformation of the code verifier that will be sent to the authorization server during the authorization request. The code challenge serves as a public commitment to the secret code verifier without revealing the verifier itself. The authorization server will store this code challenge and later verify that the code verifier provided during token exchange matches this commitment. The PKCE specification defines two code challenge methods, plain and S256. The plain method simply uses the code verifier as the code challenge without any transformation. However, this method provides minimal security benefits and is only included in the specification for backward compatibility with constrained environments that cannot perform SHA-256 hashing. The S256 method is the recommended and widely used approach. It generates the code challenge by taking the SHA-256 hash of the code verifier and then Base64 URL encoding the resulting hash. The SHA-256 hash function produces a 256-bit output which is 32 bytes, and this is then converted to a Base64 URL safe string. Let me explain the exact mathematical operation with a concrete example. Suppose our code verifier is the string beginning with db and ending with xk. First, we compute the SHA-256 hash of this string. SHA-256 will produce a 32-byte hash value. In hexadecimal representation, this hash might be beginning with E9 and ending with CM. However, we do not use the hexadecimal representation in PKCE. Instead, we take the raw 32 bytes from the SHA-256 operation and encode them using Base64 URL safe encoding. Base64 URL safe encoding uses the same Base64 algorithm but replaces plus signs with hyphens and slashes with underscores, and removes padding equals signs to make the result safe for URL transmission. In Python, you would use the hashlib module for SHA-256 hashing. First, encode the code verifier string to bytes using UTF-8 encoding. Then compute the SHA-256 hash using hashlib.sha256. Get the digest as raw bytes, and finally encode those bytes using Base64.URL safe B64 encode. Remember to strip any padding equals signs and decode to a string. In JavaScript, you use the Web Crypto API's subtle.digest method with the SHA-256 algorithm. This returns a promise that resolves to an array buffer containing the hash bytes. You then convert this to a uint8 array and Base64 encode it using the same URL safe conversion we used for the code verifier. In Java, you use the message digest class with the SHA-256 algorithm, compute the hash bytes, and encode them using the URL safe Base64 encoder without padding. The resulting code challenge is what gets sent to the authorization server in the authorization request. Because it is a one-way hash, an attacker who intercepts the authorization request and sees the code challenge cannot reverse engineer the original code verifier. When the authorization server later receives the code verifier during token exchange, it can independently compute the code challenge using the same SHA-256 and Base64 operations, then compare it to the code challenge it stored from the authorization request. If they match, the authorization server has cryptographic proof that the client exchanging the code is the same client that initiated the authorization flow. Step 3. Build authorization request. With the code verifier and code challenge generated, we are ready to build the authorization request. This is the HTTP request that redirects the user to the authorization server to authenticate and grant consent. The authorization request is a GET request to the authorization server's authorization endpoint, and all parameters are passed as query parameters in the URL. Let us examine each parameter in detail because getting these parameters correct is critical for a successful OAuth flow. The first required parameter is response_type, which must be set to code for the authorization code flow. This tells the authorization server that we want it to return an authorization code rather than tokens directly. The client ID parameter identifies your application to the authorization server. You obtain this client ID when you register your application with the authorization server. For example, if you are integrating with Google OAuth, you would register your app in the Google Cloud Console and receive a client ID that looks like beginning with 74 and ending with com. The client ID is not secret and can be embedded in your application code. The redirect URI parameter specifies where the authorization server should redirect the user after authentication. This URI must exactly match one of the redirect URIs you registered with the authorization server when setting up your application. For security reasons, the authorization server will reject any redirect URI that does not match the registered values. For mobile apps, this is typically a custom URL scheme like myapp://callback. For web apps, it's an HTTPS URL like https://myapp.example.com/auth/callback. The scope parameter specifies what permissions your application is requesting. Scopes are space-separated values that define the access level. For example, OpenID profile email requests access to the user's OpenID Connect profile and email address. Different authorization servers define different scopes. Google might have scopes like https://www.googleapis.com/auth/drive.read only for read-only drive access. The state parameter is a critical security feature that helps prevent CSRF attacks. Generate a random string at least 32 characters long using a cryptographically secure random generator, and store it in your session. When the authorization server redirects back to your application, it will include this state value, and you must verify it matches what you originally sent. If the state values do not match, reject the authorization response as it may be an attack. The code challenge parameter is where we send the code challenge we generated in the previous step. This is the Base64 URL encoded SHA-256 hash of the code verifier. The code challenge method parameter specifies how the code challenge was generated. This should always be S256 unless you are in a constrained environment that cannot perform SHA-256 hashing, in which case you would use plain. Some OAuth implementations also support optional parameters. The prompt parameter can control authentication behavior. Setting it to login forces re-authentication, even if the user has an active session. Setting it to consent forces the consent screen to be displayed. The login_hint parameter can pre-fill the username or email field on the authentication page to improve user experience if you already know the user's identifier. The nonce parameter is used in OpenID Connect flows to associate client sessions with ID tokens and prevent replay attacks. It is a random string that will be included in the ID token for validation. Authorization request example. Now let us look at a complete, real-world example of an authorization request with actual parameter values. This will help solidify your understanding of how all these parameters come together in practice. We will use a fictional application called MyTaskApp that is integrating with a generic OAuth provider called Auth Provider. Let's say our client ID is beginning with A1, ending with H8, which we received when we registered MyTaskApp with Auth Provider. Our registered redirect URI is https://mytaskapp.com/callback. We want to request access to the user's profile information and their task list, so our scopes will be OpenID profile tasks:"read tasks:"write. We've generated a code verifier beginning with DB, ending with XK, and computed its SHA-256 hash and Base64 URL encoded it to get the code challenge beginning with E9, ending with CM. We've also generated a random state value beginning with XY, ending with 56, for CSRF protection. The complete authorization URL would start with the authorization server's authorization endpoint. For Auth Provider, this is https://auth.authprovider.com/OAuth/authorize. Then, we append all our query parameters. The full URL includes the base endpoint followed by these parameters. !response_type =code. and sign client underscore ID equal beginning with a 1 ending with H8. And sign redirect underscore URI equal https://mytaskapp.com/callback. And sign scope equal open ID space profile space tasks read space tasks write. And sign state equal beginning with XYZ ending with 456. And sign code underscore challenge equal beginning with E9 ending with CM. And sign code underscore challenge underscore method equal S256. Notice how the redirect URI is URL encoded. The colons, slashes, and other special characters in the URL are converted to %encoded format. The scope parameter uses %20 for spaces between scope values, and the colon in tasks read is encoded as %3a. URL encoding ensures these parameters are safely transmitted without breaking the query string structure. When building authorization URLs, always use your programming language's URL encoding functions rather than manually encoding. In Python, you would use lib.parse.url encode. In JavaScript, you would use the URL search params API or encode URI component. In Java, you would use URL encoder.encode. In your application code, you construct this URL with all parameters, then redirect the user to it. For web applications, this is typically done with an HTTP 302 redirect response or by setting window location href in JavaScript. For mobile applications, you open this URL in a secure browser like AS Web Authentication Session on iOS or Chrome Custom Tabs on Android. These secure browsers provide session isolation and ensure the user is authenticating with the real authorization server, not a phishing page within your app. Once the user is redirected to this URL, they leave your application and land on the authorization server's authentication page, which is completely controlled by the authorization server and outside of your application's control. User authentication and consent. After the user is redirected to the authorization server with our authorization request, several important steps happen on the authorization server side. Understanding these steps helps you design better user experiences and troubleshoot authentication issues. First, the authorization server validates the authorization request by checking all the parameters we sent. It verifies that the client ID is valid and corresponds to a registered application. It checks that the redirect URI exactly matches one of the URLs registered for this client. If the redirect URI doesn't match, the authorization server will display an error directly to the user rather than redirecting, because it can't trust where to send the user. The authorization server also validates the code challenge method as either S256 or plain, and stores the code challenge for later verification during token exchange. If all parameters are valid, the authorization server proceeds to authenticate the user. Authentication is the process of verifying the user's identity. The specific authentication method depends on the authorization server's configuration and policies. The most common method is username and password, where the user enters their credentials on a login form. However, modern authorization servers support many authentication methods. For example, they support multi-factor authentication, where users must provide a second factor like a code from an authenticator app or SMS. Other methods include biometric authentication, which uses fingerprints or facial recognition on mobile devices. Social login, where users authenticate using their existing Google, Facebook, or other social media accounts. Or passwordless authentication, using magic links sent via email or authentication apps. The authorization server may also check for an existing session. If the user has recently authenticated with the authorization server for another application or in another tab, the authorization server might have a valid session cookie. In this case, the user won't need to enter credentials again, providing a seamless single sign-on experience. This is why when you've logged into Google in one tab, other applications using Google OAuth might not require you to log in again. The authorization server evaluates session validity, session timeout policies, and the prompt parameter from the authorization request. If the prompt parameter was set to log in, the authorization server forces re-authentication even if a session exists. After successful authentication, the authorization server presents a consent screen to the user. The consent screen is a crucial privacy and security feature that informs users exactly what permissions the application is requesting. The screen typically displays the name and logo of your application, as registered in the authorization server. It also presents a list of specific permissions requested, based on the scopes you specified. These often come with human-readable descriptions, for example, access your email address or read and write tasks. Finally, the screen provides options for the user to approve or deny the request. Some authorization servers allow users to selectively approve certain scopes while denying others. The consent screen serves multiple purposes. It provides transparency about what data the application can access, gives users control over their data, and helps prevent malicious applications from gaining unauthorized access. For trusted first-party applications, the authorization server might skip the consent screen, particularly if the user has previously consented to these same scopes. Some authorization servers also support the prompt equals consent parameter, which forces the consent screen to be displayed even if the user has previously consented. Once the user clicks the Approve button on the consent screen, the authorization server generates an authorization code and prepares to redirect the user back to your application. Authorization response with code. Authorization response with code. After the user successfully authenticates and grants consent, the authorization server generates an authorization code and redirects the user back to your application. This authorization code is a short-lived, single-use credential that your application will exchange for tokens. Understanding the authorization response structure and how to handle it securely is critical for implementing OAuth correctly. The authorization server generates an authorization code that is typically a random string between 30 and 60 characters long. The code is cryptographically random to prevent guessing attacks. The authorization code has several important security properties. First, it must be short-lived, typically valid for only 60 seconds to 10 minutes depending on the authorization server's security policies. This short lifetime limits the window of opportunity for attackers to intercept and use the code. Second, the code must be single-use only. Once the code has been successfully exchanged for tokens, any subsequent attempt to use the same code must be rejected by the authorization server. Some authorization servers will revoke all tokens issued to that code if they detect a reuse attempt, as this indicates a potential security breach. The authorization server constructs the redirect response by taking your redirect URI and appending query parameters. The code parameter contains the authorization code. The state parameter contains the same state value you sent in the authorization request. This allows you to verify the response corresponds to the request you initiated and prevent CSRF attacks. If you requested OpenID Connect scopes, some authorization servers might also include an ID token as a fragment parameter, though this is less common in the authorization code flow. The complete redirect URL would look like https://mytaskapp.com/callback code equals AUTH_CODE_HERE and sign state equals XYZABC1, 2, 3 random state 4, 5, 6. The authorization server performs an HTTP 302 redirect response, which instructs the user's browser to navigate to this URL from the user's perspective. They are immediately returned to your application. The user's browser makes a GET request to your redirect URI with these query parameters. Your application must now handle this callback request. The first critical security check is validating the state parameter. Extract the state value from the query parameters and compare it to the state value you stored in the session or memory when you initiated the authorization request. If these values don't match, immediately reject the response and terminate the flow. A state mismatch indicates either a CSRF attack or a corrupted flow. After validating the state, extract the authorization code from the code query parameter. This code is precious. Treat it as a sensitive credential. Never log it, Never display it to users, and never transmit it over insecure channels. The code is bound to your client ID, redirect URI, and the code challenge you sent in the authorization request. This binding is what makes PKCE secure. An attacker who intercepts the authorization code cannot use it without also having the code verifier. Your application stores this authorization code temporarily, typically in memory or secure session storage, and immediately proceeds to exchange it for tokens at the authorization server's token endpoint. The authorization code should be used as quickly as possible given its short lifetime, typically within seconds of receiving it. Now we reach the critical token exchange step, where the client exchanges the authorization code for actual tokens. This is where PKCE verification happens. Unlike the authorization request, which was a simple redirect GET request, the token exchange is a direct backend-to-backend POST request to the authorization server's token endpoint. The request must be made over HTTPS to protect the authorization code and code verifier in transit. The token request is sent as an HTTP post with the content type header set to application/xww form URL encoded, meaning the parameters are sent in the request body as form data. Let us examine each required parameter. The grant_type parameter must be set to authorization_code to indicate we are using the authorization code flow. This tells the authorization server how to process the request. The code parameter contains the authorization code we received in the redirect. This is the single-use credential that proves the user authorized our application. Remember, this code is short-lived and must be used quickly. The redirect URI parameter must exactly match the redirect URI that was sent in the authorization request. The authorization server will verify this match as a security measure. Although the authorization code is already bound to the redirect URI, sending it again allows the authorization server to verify the binding. The client ID identifies our application, the same client ID that was used in the authorization request. For public clients using PKCE, you do not need a client secret. For confidential clients, you would also include client authentication, typically via client secret parameter or HTTP basic authentication in the authorization header. The code verifier parameter is the star of PKCE. This is the original random string we generated at the very beginning, before the authorization request. Remember, we sent the code challenge, the SHA-256 hash of this verifier, to the authorization server during authorization. Now we are revealing the actual verifier. The authorization server will take this verifier, compute SHA-256 of the code verifier, Base64 URL encoded, and compare it to the code challenge it stored earlier. If they match, the authorization server knows with cryptographic certainty that the client making this token request is the same client that initiated the authorization flow. An attacker who intercepted the authorization code would not have the code verifier and therefore could not complete this step. Token exchange HTTP request example. Let's examine the exact HTTP request format for the token exchange with a concrete example. This is a POST request to the authorization server's token endpoint. The endpoint URL varies by provider. For example, Google uses https://auth2.googleapis.com/token. Auth0 uses https://your_domain.auth0.com/oauth/token. And GitHub uses https://github.com/login/oauth/access_token. You'll find the token endpoint URL in the authorization server's discovery document or documentation. The HTTP headers are critical. The content type header must be application/x-www-form-URL encoded because we are sending form data. The accept header should be application/JSON to indicate we want JSON responses. Some authorization servers also require or recommend a user agent header identifying your application. For confidential clients, you would include an authorization header with HTTP basic authentication containing the client ID and client secret, but for public clients using PKCE, this is typically omitted. The request body contains URL encoded form parameters. Each parameter is formatted as key equal value and parameters are joined with ampersands. Special characters must be URL encoded. For example, our redirect URI https://mytaskapp.com/callback becomes https://3a%2f%2f mytaskapp.com%2f callback. The complete HTTP request would look like this. A post to /OAuth/token, using HTTP/1.1. It would have a host header pointing to auth.authprovider.com, a content type of application /x-www-form-URL encoded, a content length showing the body size, and an accept header of application/JSON. Token response structure. When the authorization server successfully validates the token request, it responds with a JSON payload containing multiple tokens and metadata. Let's examine the structure of this response and understand what each field means. The response has a 200 OK HTTP status code and content type application/JSON. The JSON body contains several important fields that your application must parse and handle correctly. The access token field contains the access token, which is the primary credential for accessing protected resources. This is what you'll send to resource servers to prove you're authorized to access the user's data. Access tokens can be in different formats. Some authorization servers use random opaque tokens that are just random strings with no internal structure. Other authorization servers use JSON web tokens, or JWTs, which are self-contained tokens with embedded claims. We'll examine JWT structure in detail shortly. Access tokens have limited lifetimes for security, typically ranging from 15 minutes to 1 hour, though some systems use longer durations. The token type field specifies how to use the access token. This is almost always bearer, which means you include the token in an authorization header with the format authorization:bearer access token. The bearer token type is defined in RFC 6750. Some older systems might use different token types, but bearer is the OAuth 2.0 standard. The expires in field tells you how many seconds until the access token expires. This is not an absolute timestamp but a relative duration from the time the token was issued. For example, expires in :3600 means the token expires in 3600 seconds or 1 hour. Your application should track when tokens were issued and refresh them before expiration. The refresh token field contains a refresh token, which is an optional long-lived credential that can be used to obtain new access tokens without requiring the user to re-authenticate. Not all OAuth flows issue refresh tokens, and some authorization servers only issue them to confidential clients or when specific scopes are requested. Refresh tokens don't expire automatically but can be revoked by the user or authorization server. They should be stored very securely, as they provide long-term access to user resources. The scope field returns the actual scopes that were granted. This might differ from what you requested if the user denied some permissions or if the authorization server doesn't support certain scopes. Always check this field to confirm what access you actually received. For OpenID Connect flows, there's also an ID token field containing a JWT with identity information about the authenticated user, including claims like the user's unique identifier, email address, name, and authentication timestamp. Access token structure JWT format. Many modern authorization servers issue access tokens in JSON Web Token, or JWT, format. Understanding JWT structure is crucial because it affects how you validate and use these tokens. AJWT is a self-contained token that includes all the information needed to verify its authenticity and extract claims about the user and authorization. JWTs are particularly popular because resource servers can validate them without making calls back to the authorization server, enabling stateless, scalable architectures. AJWT consists of three parts separated by dots: the header, the payload, and the signature. Each part is Base64 URL encoded. The complete token looks like, beginning with EY and ending with 5C. Let me break down each part with a real example. The header is the first part before the first dot. When Base64 decoded, it contains JSON with metadata about the token. The ALG field specifies the signing algorithm, commonly RS-256 for RSA with SHA-256. ES-256 for ECDSA with SHA-256, or HS-256 for HMAC with SHA-256. The TYP field is always JWT. Some headers also include a KID or key ID field that identifies which key the authorization server used to sign the token, which is essential when the server rotates keys. An example decoded header would show the ALG field as RS-256, the TYP field as JWT, and the KID field as 20210501. The payload is the second part between the two dots. When Base64 decoded, it contains JSON with claims about the token and the user. Standard claims include ISS for issuer, which identifies the authorization server that issued the token. Sub for subject, which is the unique user identifier. AUD for audience, which specifies which resource server should accept this token. Express for expiration time as a Unix timestamp. IAT for issued at timestamp. NBF for not before timestamp, indicating when the token becomes valid. And JTI for JWT-ID, which is a unique identifier for this specific token. Custom claims can include anything the authorization server wants to communicate. The signature is the third part after the second dot. It is created by taking the encoded header and encoded payload, concatenating them with a dot, and then signing this string using the algorithm specified in the header and the authorization server's private key. For RS-256, this involves computing an RSA signature using SHA-256. The signature ensures that the token has not been tampered with and proves it was issued by the authorization server. Anyone with the authorization server's public key can verify the signature, but only the authorization server with the private key can create valid signatures. This is what makes JWTs secure and enables stateless validation. ID token structure and claims. In OpenID Connect, which is built on top of OAuth 2.0, the token response includes an ID token alongside the access token. The ID token is always a JWT that contains identity information about the authenticated user. While the access token is for authorizing API requests, the ID token is specifically for verifying the user's identity. Understanding the distinction is important. Access tokens are for authorization. ID tokens are for authentication. The ID token structure follows the same three-part JWT format: header, payload, and signature. However, the payload contains specific claims defined by the OpenID Connect specification. Let's examine the standard claims. The ISS issuer claim identifies the OpenID provider that issued the token and must match the expected issuer URL. The sub-subject claim is a unique identifier for the user that is locally unique to the issuer and never reassigned. This is the primary user identifier you should use. The AUD audience claim must contain your client ID and sometimes includes other audiences. You must validate that your client ID is present in the audience. The express expiration claim specifies when the ID token expires as a Unix timestamp. ID tokens are typically short-lived, often 5 to 60 minutes. The IAT claim indicates when the token was issued. The nonce claim is critical for security. It must match the nonce value you sent in the authorization request. This binds the ID token to your specific authentication request and prevents token replay attacks. If you sent a nonce in the authorization request, the ID token must contain it, and you must validate it matches. The auth time claim indicates when the user authentication occurred, which is useful for determining if re-authentication is needed for sensitive operations. The ACR authentication context class reference describes the authentication methods used, such as single-factor or multi-factor authentication. Refresh token usage. Refresh tokens are long-lived credentials that allow your application to obtain new access tokens without requiring the user to re-authenticate. They are a critical part of maintaining long-running sessions while keeping access tokens short-lived for security. Understanding when and how to use refresh tokens is essential for building robust OAuth 2.0 applications. Refresh tokens are opaque strings with no defined structure in the OAuth specification. They are typically random tokens stored in the authorization server's database, associated with the user, client, and granted scopes. Unlike access tokens, which might be JWTs that can be validated locally, refresh tokens always require a callback to the authorization server for validation and token issuance. This gives the authorization server centralized control over token refresh and allows it to enforce policies, like rate limiting or revocation. When should you use a refresh token? The typical flow is: your application receives an access token with an expires in value, stores this expiration time, and before the access token expires, ideally with a buffer of a few minutes, makes a token refresh request to get a new access token. You can also attempt to use the access token, and if the resource server returns a 401 unauthorized response indicating the token is expired or invalid, immediately use the refresh token to get a new one. This is called reactive refresh, while proactive refresh based on expires in is called predictive refresh. Combining both strategies provides the best user experience. To use a refresh token, you make a post request to the same token endpoint you used for the authorization code exchange. The grant underscore type parameter is set to refresh token instead of authorization code. The refresh underscore token parameter contains your refresh token. The client ID identifies your application. For confidential clients, you also include client authentication. Optionally, you can include a scope parameter to request a narrower set of scopes than originally granted. Refresh tokens should be treated with extreme care. Store them securely, preferably encrypted. Never expose them in URLs or logs. Implement refresh token rotation if your authorization server supports it. Token validation process. Properly validating tokens is one of the most critical security aspects of OAuth 2.0 implementation. Many security vulnerabilities in OAuth arise from insufficient token validation. Let's walk through the complete validation process for each token type, starting with JWT access tokens and ID tokens, then covering opaque access tokens. For JWT tokens, validation requires multiple steps, all of which must succeed before you can trust the token. First, parse the JWT into its three components: the header, the payload, and the signature. Verify the token has not been tampered with by validating its signature. For RS-256 tokens, retrieve the authorization server's public key, typically from its JSON Web Key Set, or JWKS endpoint. The JWKS is usually available at a well-known URL, for example, https://auth.provider.com/.wellknown/jwks. After signature validation, verify the claims. Check the ISS issuer claim matches your expected authorization server URL exactly. Check the AUD audience claim contains your client ID or resource server identifier. For ID tokens, this is your client ID. For access tokens, this should be your API identifier. Verify the EXP expiration timestamp is in the future. Current Unix time must be less than the EXP value. For opaque access tokens, which are just random strings, validation is different. The resource server must make an introspection request to the authorization server's introspection endpoint, typically at /OAuth/introspect. This is a POST request with the token in the body. The authorization server responds with JSON indicating if the token is active and returning associated metadata like the user identifier, client ID, scopes, and expiration. Additional security checks include verifying the token isn't on a revocation list if you maintain one, checking that the scopes in the token are sufficient for the operation being performed. How PKCE prevents interception attacks. Now let's examine exactly how PKCE prevents authorization code interception attacks, which is the primary threat it was designed to address. Understanding the attack scenario and how PKCE mitigates it will deepen your appreciation for this elegant security mechanism. The authorization code interception attack is particularly dangerous for mobile and single-page applications where the authorization code is transmitted via redirects that can be intercepted. Here is the attack scenario without PKCE. A malicious app on a user's mobile device registers a custom URL scheme that matches or closely resembles a legitimate app's redirect URI. When the user authorizes the legitimate app, the authorization server redirects the user back with the authorization code. The malicious app intercepts this redirect by handling the URL scheme. The attacker now has the authorization code. In traditional OAuth without PKCE, the attacker could exchange this code for tokens if they also had the client secret. But public clients like mobile apps cannot securely store client secrets. They are embedded in the app binary and can be extracted through reverse engineering. So the client secret provides no real protection for public clients. PKCE eliminates this vulnerability through its cryptographic challenge response mechanism. Let's trace through how PKCE prevents the attack. When the legitimate app starts the flow, it generates a random code verifier and computes the code challenge. The code verifier stays on the legitimate app. It's never transmitted during the authorization request. Only the code challenge, which is a hash of the verifier, is sent to the authorization server. The authorization server stores this code challenge associated with the authorization code it will issue. When the user authorizes the app, the authorization server returns the authorization code via redirect. Even if the malicious app intercepts this redirect and obtains the authorization code, the attacker is stuck. The authorization code alone is worthless. When the attacker tries to exchange the authorization code for tokens, they must provide the code verifier. But they do not have it. The code verifier was never transmitted over the network. It stayed secure on the legitimate app. The attacker cannot compute the code verifier from the code challenge because SHA-256 is a one-way cryptographic hash function. There is no way to reverse the hash and recover the original verifier. Without the correct code verifier, the authorization server's token endpoint will reject the exchange request. The authorization server computes SHA-256 of the provided code verifier, compares it to the stored code challenge, and when they do not match, refuses to issue tokens. This is the brilliance of PKCE. It provides cryptographic proof that the client exchanging the authorization code is the same client that initiated the authorization request, without requiring any pre-shared secrets that could be compromised. Security best practices. Implementing OAuth 2.0 with PKCE correctly requires following numerous security best practices beyond just the protocol mechanics. Let's examine the critical security measures you must implement to build a secure OAuth integration. These practices address various attack vectors and vulnerabilities that could compromise your application even when PKCE is properly implemented. First, always use HTTPS for all OAuth communications. The authorization request redirect can use HTTPS or custom schemes for mobile apps, but the token exchange must always use HTTP pages. Never make token requests over HTTP. The authorization code and code verifier are sensitive credentials that must be protected in transit. Second, implement proper state validation to prevent CSRF attacks. Generate a cryptographically random state parameter of at least 32 characters, store it in your session, and verify it matches when handling the authorization response. If the state doesn't match, reject the response immediately. The state parameter is your defense against cross-site request forgery attacks where an attacker tricks a user into completing an OAuth flow for the attacker's account. Third, use the strongest code challenge method available. Always use S256 unless you are in a severely constrained environment that cannot perform SHA-256 hashing. The plain method provides minimal security benefits. Fourth, validate redirect UR is strictly on the authorization server side. Only allow exact matches with pre-registered URIs. Do not use wildcard matching or pattern matching, as these can be exploited. The redirect URI is a critical security parameter, and loose validation enables open redirect vulnerabilities. Fifth, keep authorization codes short-lived. The recommendation is 60 seconds to 10 minutes maximum. Shorter is better. The authorization code is vulnerable during the redirect window, so minimizing its lifetime reduces the attack surface. Sixth, implement single-use authorization codes and detect reuse attempts. If an authorization code is used more than once, it may indicate an interception attack. Some authorization servers automatically revoke all tokens issued to that code upon detecting reuse. Summary and conclusion. We've completed our comprehensive journey through OAuth 2.0 Authorization Code Flow with PKCE. Let's recap the key concepts and takeaways. OAuth 2.0 is an authorization framework that enables applications to obtain limited access to user resources without exposing user credentials. The authorization code flow with PKCE is the most secure OAuth flow and is recommended for all application types, including mobile applications, single-page applications, and traditional web applications. PKCE enhances security through a cryptographic challenge response mechanism. The client generates a code verifier. It then computes its SHA-256 hash as the code challenge. The client sends this challenge during authorization, and provides the verifier during the token exchange. The authorization server verifies that the verifier hashes to the challenge, providing cryptographic proof that the same client completed both steps. This prevents authorization code interception attacks without requiring client secrets, making it perfect for public clients. The complete flow involves 8 main steps: generate code verifier and challenge, redirect user to authorization endpoint with all required parameters including code challenge, user authenticates and grants consent at the authorization server, authorization server returns authorization code via redirect, client validates state parameter for CSRF protection. Client exchanges authorization code plus code verifier for tokens. Authorization server verifies PKCE and issues access token, ID token, and refresh token. And finally, the client uses access tokens to access protected resources. Each step involves specific HTTP requests with precise parameters that must be correctly formatted and validated. Access tokens authorize API requests and can be opaque strings or JWTs with embedded claims. ID tokens provide identity information about the authenticated user and are always JWTs with standard OpenID Connect claims. Refresh tokens enable obtaining new access tokens without re-authentication and should be stored securely and used carefully. Security best practices include always using HTTPS, implementing proper state validation for CSRF protection, using S256 code challenge method, strictly validating redirect URIs, keeping authorization codes short-lived, implementing single-use codes, storing refresh tokens securely with encryption, performing thorough token validation, using appropriate token lifetimes with short-lived access tokens, implementing rate limiting, monitoring for suspicious patterns, and staying current with OAuth security recommendations. Thank you for your attendance. Please consider subscribing to the channel.